welcome to another interesting episode in this series of your math class. Today, as we see on the screen, we are going to study functions. Functions is a continuation to the topic of relations, right? If you might have seen my previous video on relations, you might have the link to continue on this topic today. Else, you may revisit the previous video on relations and then come to this topic because it requires some foundation of relations to understand, the special case in which functions fits into, right? So let's take a whiteboard and understand it right away. So when you talk about functions, let's revisit relations first, right? So we know that a relation is basically a mapping between, say, A and B. So if A has, say, A, B, C, and B has D, E, F, a relation, now this is an additional concept which we might not have discussed in the last video, that a relation can be like, say, one-on-one, or like one to many, right? Or like many to one, or like many to many, right? So one to one, one to many to one, and many to many. But then a function is a special kind of a relation where these two do not exist. So a function is a special kind of a relation where every element on this side can map to only one element on this side, right? So a one to many and a many to many cannot exist. A one to one can exist or many to one can exist. So like let's take, for example, the function y equals x squared, where x and y both belong to, say, natural numbers, right? So here, your x, this is your x and this is your y. So x can be like, say, 1, 2, 3, right? 4 to infinity. And your y can be like the square of 1. But now, practically, your y can have any 1, 2, 3, 4, 5, 6, right? But here, since it's y equals x squared, so y can only be a perfect square here, right? So like 4 can have 2. 2 can map to 4 because 4 is the square of 2. 1 can map to 1 because 1 is the square of 1. Similarly, like if this goes to till 16, this 9 and 16. So 9 can map to 3, 4 can map to 16. So here you see there are some elements which do not have a mapping here. But then if you look at this, every element from this is exactly mapping to one element here, right? Now, if you extend this x to include even negative numbers, then you can have, say, -1, -2, -3, 1, 2, 3. And over here, -1 square is 1, -2 square is 4, -3 square is 9. And then even 1, the square of 1 is 1, the square of 2 is 4, the square of 3 is 9. So you see, each of these map to only one element here. It can't be possible that -1 maps to 1 as well as something else, right? There's no something else here. So such kind of a relation is a function. Right? So now we know what a function is, right? A special kind of relation where every element from this side maps to only one element on this side. And when we talk about these sides, right, they have a special name here. So now we come to some definitions called as a domain, then a codomain, and then a range. Okay, now let's see all these three together. Let's take the same function, y equals x squared, where x and y both belong to natural numbers, all right? That's the constraint here. So now technically, this is your x and this is your y. So technically it's given here that your y and x can both belong to natural numbers. So your y can also be like 1, 2, 3, dot, dot, like say 9, 16, 23, 29, right? All these are natural numbers. You know, x can be again 1, 2, 3, 4, 5, dot, 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 whatever, goes down until infinity, right? So technically y can be any natural number, x can be a natural number, right? So the domain of the function, so this side where you provide the inputs, the input here is 1 and the output is 1. Input is 2, output is 4, right? Input is 3, output is 9. So input is 1, output is the square of 1, which is 1. Input is 2, and output is the square of 2, that is 4. So the inputs are called as a domain. So all possible values that the inputs can possess are called as a domains. And here, the codomain is basically all possible values that the output can theoretically come under, because here it's given that x and y both belong to natural numbers, right? It's given here in the definition. So y can be any natural number, theoretically. But then practically, if you look at it, these values like 2 and 3, if you want these values to be complying with this equation, like y equals x squared, then in this case, if you take y equals 2, then x is going to be plus or minus square root of 2. So this is not a natural number. So practically, y cannot be anything apart from a perfect square, right? So this means that the possible values which y can take cannot be all natural numbers, but it's going to be some subset of these natural numbers, right? And this subset is basically called the range. So the range of the function is basically the set of all possible values which y can attain. So that's basically 1, 4, 9, 16, 25, so on and so forth. So all these are natural numbers, but not all the natural numbers. It doesn't have 2, 3, 5, 7, 8, right? Because they're not perfect squares. So a range is a subset of a codomain. Okay, keep this in mind. Now there is a special case when the range will be equal to the codomain. We'll take that case later. But that's basically domain, codomain, and range for you, right? Now let's look at the different types of functions. Right? The first one is called as a one-to-one function. What is a one-to-one function? Let's say y equals 2x plus 1. Okay. So if you draw this function here on a graph, it looks like a straight line like this, isn't it? So every element in x maps to exactly one element in y. If you take any x projected here, it has exactly one value of y, right? So if x is equal to 1, then y is equal to 2 into 1 plus 1, which equals 3, right? If x equals 2, then y equals 2 into 2 plus 1, which equals 5, right? So like this, every value of x maps to exactly one value of, every value of x, yes, maps to exactly one value of y, right? So there's no many to one mapping over here. The point I'm trying to make is, unlike the function like y equals x squared, if you draw this on a graph here, right, it looks something like this, right? So here, two values of x map to one value of y, like say -1 and +1, both have the square as 1. -3 and +3, both have their square as 9, right? So this is a many-to-one function. Unlike that, this is a one-to-one function, okay? So that's an example of a one-to-one function. Now the second one is on-to function. What is an onto function? An onto function is one. Again, let's take the example y equals, say, sine of x, okay, a trigonometric function this time. So if I plot this here, right, it looks like this. Yeah, sinusoidal curve, right? This is 0. This is pi by 2, right, which is 90 degrees in the radians. This is again pi, right, so on and so forth. So here you see that every value of y definitely has a corresponding value in x. right? There's no value on this y coordinate which does not have any x over here, right? So if you draw it like this, the domain and the codomain, x and y, x can be a, b, c, d, e, y can be again like say u, v, w, x, y. So u will have some mapping here, v will have some mapping here, w will have something. It's quite possible that two numbers can map to a particular value, but each of these values here will have something on the other here. There's going to be no solitary values like this, which has nothing mapped, right? So such a function is called as an onto function, right? And then the third one is 1, 1 and onto. So as the names imply, it's both 1, 1 as well as onto. Like the function, like say y equals 3x plus 2, right? This is a 1, 1 function as well as an onto function, all right? So just for namesake, a 1, 1 is called as an injective function. And onto is called as a surjective function. And a 1, 1 and onto is called as a bijective function, right? So just keep these names somewhere in your diary. Injective is 1, 1, surjective is onto, and bijective is 1, 1 and onto, right? So this is it to introduce you to functions. I hope this discussion was interesting. There is a lot more to this, but then this is going to get you started on functions. Again, if you have any questions, let me know in the comments box at the bottom of the video. And if you want to revisit this concept, please feel free to pause the video or reduce the speed and then watch the video once again, all right? So until then, I wish you good luck with your studies. Take care and see you again in another episode with another interesting topic. Until then, take care. Bye-bye. If you like this video, please press the like button. For more such videos, subscribe to the channel. If you have suggestions for a new topic and would want to see a video made on that topic, please feel free to comment in the comment section below. Thanks for watching the video and see you in another video. Bye bye.